Good morning, everybody. Okay, welcome to this new section. Sorry if we are late 15 minutes, but this is Spanish time. We are perfect time, actually. Okay, let's introduce, it's a pleasure to introduce Professor Elena Berdisheva from University of Cape Town, South Africa. And she's going to speak about the metric approximation of set-valued functions on bounded variation by integer operators. Please.
Thank you very much, and thank you, the organizers, for inviting me here. I am an outsider also in terms of community, also in terms of the topic, as you will see. Well, I will try to do my best to explain what one of the areas I'm working in. So it will be a long introduction about the situation and, I don't know, some short path with theorems. This is, let me see. This is joint work with a group from Tel Aviv, Nirodin, Elsa Varhel, and Hofer. Okay, we are going to, let me return back, metric approximation of set-valued functions. So I'm going to explain you first what set-valued functions are, in particular setup what we consider, and what metric approximation is. So I denote by this capital T over D, the collection of compact non-empty subsets over D. And we consider the following setup, set-valued functions for us, which I will frequently shorten like this, or they also live in mathematics under the name multifunctions, or functions that build a compact interval of the real life on the real line into the set. So the argument is a real number and the value is a compact non-empty set. They have plenty of applications in mathematics. I will not go into details because of lack of time. So there is some selection, dynamical system, control theory, game theory, differential inclusions, mathematical economics, optimization. Let me stop here for a moment. These are traditional areas. These are areas where, in the absolute majority of cases, the sets, our values, the sets were in addition convex. So there is a big established theory how to work with functions whose values are convex sets. And of course, convex sets are special. We have plenty of methods to work with them, like support functions, whatever. Now, this last thing coming here, geometric modeling, this is a quite modern, quite new thing. It, of course, became now very popular in connection with, digitalization everywhere. And then you can forget about convexity, because what we want to model some geometric objects, and why should they be convex? And here is, here is a picture, is an example. I copied that from a PhD student of Shay Kels, who was also a student of Nira and Elsa. So this is this problem what he, for example, considered one of the problems, that we have some three-dimensional object, and what's given is the collection of cross-sections. And then you need to recover the object from the cross-sections. One practical application would be in medical imaging. Okay? So I always say that, for example, here are two bones and some device, I don't know, let's say X-ray makes you cross-sections, but the doctor wants to see a three-dimensional object on the screen. So, and forget about convexity, it's not convex anymore. And here particularly, I'm not going to get into details, but this is some piecewise linear reconstruction and this smooth reconstruction, so there are methods. The point is that at least when we go into geometric modeling, we can forget about convexity. As I told you, convex functions are quite well studied, many work. So approximation theory, so in addition to the set-valued analysis, of course, the approximation theory also develops, and here's some selection. I don't say it's full. Richard Whittle in 1979, he adopted a classical Bernstein operator, which is an absolutely well-known, best-studied, well-understood operator in approximation theory for approximation of continuous real functions to this setup to approximate functions, set-valued functions with convex images. So I come from classical approximation theory. So to say, for me, it's something that you learn at school, at kindergarten, let's say. But I will give you formula later. It will appear later. So just some very classical operated in Nirodin, Elsevier, and many students work since 80s, completely different approaches, different things. Michele Campiti, my good friend from Italy, Krovkin type theorems. Then there is a survey by Murishan, and then one paper also, Babenko, Polishuk, some kind of trigonometric approximation. The usual problem is convexification. This means that if we apply our approximating process, then it converges. Yeah? Well, we want that it converges, but the limit is a function with convex images. So, for example, in this paper by Vitali, his construction, he shows that this sequence of Bernstein operators converges to the convex hull of the given function. So the result is always convex. And of course, it's great if your function was originally with convex images, you solve the problems, but for us, it's not what we want to have. Okay, pioneering work on approximation of set-valued functions with general, not necessarily convex images, V. Arnstein, piecewise linear approximations based on something what we later started to call metric pairs. I will immediately introduce them. So that also already has some age here, as you see, but the idea comes back to him. So what are metric pairs? I consider RD, RD, all norms on RD are equivalent, as we know, so we just grab one norm, doesn't matter which, and then I can, for a point in the set, I can introduce the distance in the usual way. Yes, so this is the closest point. Remember, my sets are convex. My sets are compact. So I always have the closest point. Here I have these two sets A and B, and here is A, and this is this is just the Euclidean norm. This is the distance between A and B. This is the point B here. This is the distance between B and A, and so on. Right? And then the set of metric pairs of two sets A and B is the set of pairs, A in one set and B in the second set, such that E is a projection, so exactly this closest point, or B is a projection of on the other side. Of course, depending on the norm, it can be a unique point. It must not be, yeah? So think about L infinity, then it can be really a continuum of points, their projections. So say if I have the situation that one point exactly realizes the distance, that this is a metric pair. This metric pair is special. This gives me exactly the Hausdorff distance. Okay, yeah, I know my problem is I can talk and talk and talk, but I need to put my talk in the frames. That's why I didn't give you here so see standard definition or one of the standard definitions of the Hausdorff metric, but this is an equivalent definition, so we just look at all metric pairs, look at the distance between them, and take the maximum. This is a Hausdorff distance. My set K over D, the set of compact, non-empty subsets over D, together with the Hausdorff metric, is the complete metric space. Okay, and the idea of Arnstein was to create a linear interpolant by connecting metric pairs by pieces of linear functions. Let me make it maybe a small picture to understand, to let you understand how non-trivial it is. So imagine these are two cross sections, and I want to. So these are two sets. I'm trying to do a three-dimensional picture. Now, how do you create linear interpolant? So clearly you take one point from the below, one point from the up, and connect them by a straight line. But what is the corresponding line? What is the corresponding point? And Arnstein answer is take a metric pair. So it would be something like this. Okay, let me check the time. The standard tools to work with sets, which is very good for convex sets again, or Minkowski linear combinations. So if I have sets and if I have scalars, then I just consider all possible linear combinations. This is the Minkowski linear combination. It has this property of convexification, and to show you how bad it is if the sets are not convex, for convex sets it's perfect, just really perfect. Let's see, I take a set A, which consists of 2.0 and 1. Yeah, so now my codomain is now K of R, compact subsets of R, yeah? 0, 1, and then I take an average of n copies. Yeah? So if you take an average, you want to see exactly the set, right? An average of n copies of the same set, I would expect I get the same set. Look what happens here. So these are 5 copies, this is the result. So it's not, of course, it's not literally a convex set, but you see what happens. Fills the gaps. Doesn't work. Yeah, so Minkowski linear combinations don't work. What is a substitute? So there was a tool developed by Nirav, Elzo, and Alona exactly right before the time I joined the team. And first I need to introduce some intermediate step. This is what we call metric chain if I have sets. So here, for example, in this picture, I have these 4 sets for intervals. Then I go over points such that 2 neighboring points are always a metric pair. So here, these red lines, they show some metric chains. So for example, this is a metric chain, this is a metric chain, here is the straight line is a metric chain, and so on. Okay, this CH is chain here, you know, it's the collection of all metric chains, and now the metric linear combination, now it comes. So exactly, I have sets, I have scalars, and I consider again linear combinations of elements, but now the elements which I take here belong to one metric chain. So it's of course a subset of the Minkowski linear combination, yeah, but the point is that we take much less points, much less combinations. And look at my example, now it works. So this was exactly my example. Each set consists of 2.0 and 1. I have only 2 metric chains here, only 2 matrix chains. Why? Because if I am at 1 and I look at the closest element in the next set, I will never be able to go to 0. I always stay at 1. And if I am at 0, then I'm always at 0. I never will be able to jump to 1. And now when I take the average, it's exactly this. Yes, so once again, I have here only 2 metric chains. So it looks appropriate. Okay, there is one point. However, the metric linear combination depends on the order of the sets, yeah, because I always look at the next, yeah, so I need to look at the metric pair, the next set. In general, is of course the restriction not for us because we're going to approximate functions, yeah, so we have some natural order of these cross sections. Integral, okay, there is developed integral for set-valued functions, again with convex images. It's the Oman integral. If I have a set-valued function, a single-valued function S is called a selection. So S of X is always an element of F of X. So if I have a graph of a function, yes, so here is a graph. This is A, this is B. The value at each point is an interval, yes, so any single-valued function like this is a selection. Yes, so this is an example of a selection. The Oman integral is the volume take all integrable selections, take all integrals. It gives you a set. This set is called the Oman integral. It's of course convex, so it's a well-known fact that the Riemann integral is always convex and compact, even if the values of f are not. Again, a modification of my example. Now, I took a function which is constant function. The value is always 0, 1. This is the graph of this function. On the interval 0, 1, let's look at its average. Here we have a really convex answer. The average is the entire interval 0, 1. Why? I just take point alpha between 0, 1. I have this red is the corresponding selection. Yeah, it's an integrable selection. The integral is exactly alpha. So it gives me all possible points here. So it filled the gap. Yeah? It's perfect. As long as you stay in the world of convex values, it's all perfect. Yeah? If you go away from convexity, it's a disaster. All right, this is what I'm telling you. Useless for work with set-valued functions with general, not necessarily convex images. Let me check the time. Okay, metric selection. So now we gain the same ideas for metric combinations. We are going to do the same for the integral, but we take much less selections in the integral so that it stops filling the gaps. Again, an intermediate step. So now you can read it, but let me better explain it. The chain function. So now I have some metric. I have a partition of the interval, and then I have some metric chain, and then this is just the piecewise constant function. So something like this. So I have a selection, I have a point, let's say start here, this would be the closest point. Okay. Of course, it can go out of the graph, it's not necessarily a selection. Yeah? Okay, now a selection is called a metric selection if it's a pointwise limit of a sequence of chain functions, such type, when the size of the partition goes to 0. And these are the right selections. We denote the set of all metric selections by this S of F. This is an example here. The red lines are selections. Metric selections are lazy selections. So you can think about it because it always looks for the closest point next to you. If there is a chance for it not to change the value, it will not change the value. So if the graph stays in the interior, if the point stays in the interior of the graph, then it's always constant. Like for example, this one, it went here, it arrived at the point it cannot continue with the same value anymore. Now it has a choice, go up or down. I pick this one, goes, and here it continues. It doesn't need to change anymore. So lazy selections. Now the class I'm going to consider, I'm going to work with, I will denote it by this capital F, is the class of set-valued functions of bounded variation with closed graphs. The variation is taken in the metric space with the Hausdorff distance. Good, closed graphs are quite usual assumption in this theory. Good news, every point has a metric selection, so there is a metric selection through every point, and the graph of the function can be understood as a collection of metric selections. So always think about it. You saw maybe in your computer science department, you know, thick cable, and if they cut it, then there are many thin cables coming out of it. Yes, so this how we think of a graph of a set-valued functions. So imagine many individual functions put together in this big graph. Nice property, it's closed under pointwise limits. A pointwise limit of metric selections is a metric selection. And this is maybe the most important thing for the analysis. Regularity of metric selections. For metric selection S in this class, we always have the variation of the metric selection is bounded above by the variation of the function. Let me explain that this is something you cannot expect in general. Okay, let me repeat this graph. So look, this is the graph of the function. Lazy selection will stay, don't change here. So this is my lazy selection. You see it's controlled by the graph. Now let's see that it doesn't work for any selection. Yeah, any selection can really unbounded variation. Or at least, well, what I'm trying to say, not well, in this picture it can. In general, there is no bound possible. Look, I can have a selection like this. And so on, yeah? You see, I can make a variation as big as I want. Yeah? So this is exactly the point. Okay, not just the property of the variation is inherited, all suitable properties, all suitable structural properties are inherited. So here I didn't want to bother you with a long set of different formulas, but let's think about moduli of continuity, whatever, some suitable, depending on the functions of bounded variation. So they are not continuous, but they have limits, of course, and right, left limits at that point. So we can have one-sided, local, whatever, quasi. So it's all controlled by the mother function, the big function. Not for just selections. Just selections can be anything. Okay, now the metric integral is defined in this way. Exactly the same, yeah, we took all possible selections and all possible integrals, but we consider here only metric selections. And of course, it gives you a much smaller set. Back to my example, again, there are just two metric selections, and the average will be exactly the set 01 as we wish. Okay, approaching what I'm going to show you actually in the last minutes, we can put a weight function here. Yeah, so it's convenient that we just not integrate the function, but we integrate the function times some scalar weight function. And now, yeah, now, as I told you, it was going to be a long introduction, and now in the last minutes, just a few words about the actual result I want to show you. Approximation operators, which are integral operators. So I have here a sequence of kernels. This is my function I want to approximate. This is a sequence of operators. And kernels must have some typical normal properties. Roughly speaking, it's localization on the diagonal so that I recover the value. Okay, here are my operators. The Bernstein-Durmai operator, this is one of those classical positive linear operators in the approximation theory. P and K or Bernstein basis polynomials. This is the kernel. Another good guy, well-known guy, is Komtarovich operator, where this would be the kernel. Yeah? So if I just use it for real functions, it's a very classical approximation theory. But what we do that we adapt them for set-valued functions via this metric integral. Yeah? So now this is a set-valued function, and this here is now a metric integral. Michele Campetti started the same, exactly the same operators, also practically the same time, but based on the Riemann integral for functions with convex images. Yeah, it was very interesting to discover, to compare these things. You cannot really compare because there's a different setups. Yeah, so you cannot compare in this sense. But it was very interesting for us to see that we were working on the same, but in two different situations. Okay, but what we started with were not that classical approximation operators, positive linear operators. Actually, we started with Fourier series. Yeah, so this was the original work. This is the Dirichlet kernel. So if I now consider this exactly for real-valued periodic functions, 2 pi periodic functions, that this gives you exactly the nth partial sum of the classical trigonometric Fourier series. So this was our way. Okay, notice, however, that we have a problem here, some small specific feature that even if my set-valued functions was periodic, like here I have two copies, and then this square with the whole is, but it can have selections which are not periodic, because if it started here, it had the whole. Okay, this point is closer, it could, but it will never come up again. So there is some small something special, but otherwise you just can think that this is a straightforward way to carry over Fourier series to set-valued functions. We Googled and Googled and Googled and Googled for hours, and we couldn't find anything. It looks like that the first attempt at all to define trigonometric Fourier series for set-valued functions, we couldn't find anything, not for convex values, nothing, yeah? So it looks like that it was really the first. We couldn't find any traces of any Fourier series on the web. Okay, I have to finish. Here this Tn stays for any of our operators. Well, these three examples, but any of them, and now to see the last thing. So we were able to show the convergence, exactly what you expect if you work in approximation theory. So if X is a point of continuity, then I have convergence of these sequences. So think about it as a nth partial sum of Fourier series in the Hausdorff metric. If f is continuous in a closed interval, then the convergence is uniform. And what happens in the jump? Yeah, functions of bounded variation, they can only have discontinuities of first order. So it's continuous, so we jump. Oh yes, we have also here, we describe the set somehow. So in the original theorem, in the first variant of the theorem, we have it described in terms of metric selections. So it's post description, the only thing is that you don't want to have this. Yeah? You want to have something, a limit described in terms of a function itself. We were not able to obtain it. So you see there's two papers. This is the trigonometric paper. This is the approximation integral operators. We're not able to. And here I just repeated this formula. You know, this is a last thing still submitted is that under some reasonable assumptions on F, we have for the limit exactly what we want to see. It's of course, it's a metric linear combination. Everything is metric. The linear combination is always metric. But this is exactly what you want to see. It's half of the left-sided limit linear combination is the half of the right sided limit. And in case of Fourier, it's exactly the Dirichlet-Jordan theorem. Okay, to get it, let's jump over this. It's not much mathematics here anyway, but let's jump it over. Thank you very much for your attention.
Thank you very much, Elena, for your nice talk. And do you have any questions or remarks?
It's quite interesting. What is about Fourier transform on real line something? Could you give some ideas?
Well, a natural equation, thank you. Yes, right now we have the entire thing on a fixed interval, on a compact interval.
Yes,
so now the next step, well, you see, I mean, I would want to see we are just starting it, but when I saw now preparing 2018, I was scared, yes? So how 6 years, like yesterday. But of course, this is the next thing to think of, so we need some kind of improper interval here to integrate from minus infinity to infinity. This because thing in our mind there.
We are working on integral operators over real line, many operators, not only Fourier. So it could be interesting how you can expand this for.
Well, yes. Well, but I tried to tell you. So if my kernel, if I have an integral operator with a kernel, and if my kernel satisfies certain assumptions, then this entire theory can be run. Yeah, so the assumptions, I didn't put them because it would be a boring long slide, with something.
And also some question about Lebesgue integrable functions. Did you think about Lebesgue integrable function, LP function, some kind of?
No, this is not a Lebesgue integral, this is a Riemann integral.
Yeah.
And the problem is, that's why we work with functions of bounded variation. We work with Riemann integral, so this integral is conceptually Riemann. But I don't see a straightforward way, so it would be some different construction.
But still TS integral. Still TS integral, for instance, for bounded variation.
There are things to think of. Yeah, well, this is why you have students, right? To drop this on students.
Thank you.
Yes, thank you.
So, any other question or remarks?
I have a question about the first part of your talk. Since uniform spaces appeared, a lot of people try to generalize things from metric spaces to uniform spaces. For example, a very well-known example is convexity. The notion of convexity was transported to metric spaces by means of convexity structures and stuff, and then it was also transported to uniform spaces. So my question is, do you know if maybe the first things that you were talking about at the beginning of your talk, like metric projections and stuff, like any of that has been transported to uniform spaces anyhow?
I don't know, thank you for this. I know that this group, exactly, I showed you the names, Babenko, Polishuk, so there are some other people, they work on some, I'm afraid to tell something wrong from my mind, and they work on some more general setup. Yes, so we would be, in our setup, we would be a special case, but I'm a little bit afraid now to talk from my mind. I usually tell, especially to one of my students, who I always make a joke is better mathematician than me, like I'm a simple metric space person. I'm a simple RD person. Yes. But thank you. I have to check here. Thank you.
Okay, thank you. Thank you for the very nice talk.
Thank you.
Okay, any other question? Okay, let me ask you just a curiosity, because you study set value function from the interval to the compact convex sets, no? In RD. But if instead of the compactness, if you require just the imaginers are bounded convex set, because
in RD, yes, of course, in RD,
this
is exactly it. Yeah, okay. we teach it in real analysis, so beginners.
Yeah,
yes.
Okay, also distance makes sense also, no? Between two sets, with two bounded sets, you can consider still outdoor distance, and then you can do the same thing, no?
Repeat it, please.
No, like when you introduce the projection between two sets, no?
Yes.
You use the outdoor distance, no? Okay.
Kind of don't understand, but okay. I ask you later. Okay. Yeah, but well, we are now in a complete metric space.
Okay.
So this is I mean, some kind of the analysis, we do it immediately in a arbitrary complete metric space, because we realize that we don't actually use any specifics of that. So if I...
Okay, in any case, we can...
Yeah, but let's talk after that. Thank you. Yeah.
Okay, if you don't have any other question, let's thanks again the speaker.
Yeah. Thank you very much. Okay, that's here. For the next speaker, it's here.
Okay, let's continue this section. The next talk will be Eureka Erikash. She's going to talk about anisotropic PDEs, some results, and several open problems. Thank you.
Thank you so much. Let me start just to thank the organizers, especially Kenny, for the invitation to be here. It's quite a pleasure to be in this beautiful place and hopefully to share with you something that I'm working with and you find it interesting as well. So I will be talking about anisotropic PDEs, meaning that, just to have the context. So we have this evolutionary situation, so we have a function that depends on time and space, and we are considering differential equations having space and time derivatives, and we are going to work on this nonlinear setting. So the most famous equations having this kind of property are the porous medium equation, so the first one here, saying that the diffusion happens by this expression here, u at the power m minus 1, and it happens independently on each space direction we are considering. If we are now considering that the problem that appears for having this nonlinearity is not related to the medium that we are working with, but with the fluid, let's say that we have a non-Newtonian fluid, what happens is that the diffusion now is given by this gradient of u, so the norm of it at the power p minus 2, meaning that the gradient of u is the set, is the vector of all partial derivatives regarding the space components of our point tx. So the green does not work here, so sorry. In these two cases, what we have is that regardless each space direction we are having, we are continuing always to have the same kind of diffusion. If we are saying that that is not the case, we can have two cases. One is called the pseudo-P-Laplacian, that is the one here, says the following. The diffusion now does not depend on the full gradient of u, but just on the specific partial derivative of u regarding xi. So this is the major difference between this pseudo-P-Laplacian and the isotropic P-Laplacian. Okay? If we ask for something worse, we have the anisotropic case, meaning that in the case of the porous medium, it means that now the exponent is different in every single direction in space. In the case of the P-Laplacian, we get what happens for the orthotropic case, let's say the pseudo-P-Laplacian. So we just have the u of xi instead of the full gradient of u in space, but also we have the difficulty of having a different exponent pi in every direction in space. Okay, so this is the usual anisotropic P-Laplacian. And there are several people working on this for several years. Even in the elliptic case, meaning that we have stationary problems, so we don't have the time derivative of our function. It does not depend on time. And I'm just naming or quoting some of them, so it's not an extensive list of people working on this. So I will try to show you, by saying nothing much, let's be real, what I've been working with. So I started to work with this anisotropic equation that was a little bit different. So I got to know the work of Antonsev and Shmarev, and they said the following. When working with this Dirichlet problem, and we have this anisotropic setting, because now the exponent, as if this is the porous medium, but the exponent is no longer a constant. It depends on space and time. And they proved that for this Dirichlet problem, if this gamma is a bounded function bigger than -1, then they proved existence and uniqueness for the solution and several properties for the solutions. What they did not prove was regularity. Okay, and that was the topic of my PhD. So this was part of my PhD thesis several years ago, and that was precisely my point now, at that moment, was to show what one could say about regularity for the solutions of this kind of equations. And under the setting where we define what we mean by a local weak solution, and if you are familiar in this case of working with PDEs, it is quite striking the way that you say that you are working with a solution, because there are different definitions of solutions. So in this case, considering local weak solutions to be a bounded solution, it is not something that is quite not expected when trying to prove regularity. We always start with saying that we have a bounded function, so this is not something, but asking for some regularity assumptions, meaning that this assumption here for u allow us to say that this first integral and this one have a meaning here and are bounded. And the second regularity assumption on u allow us to say that this second integral here is also something that has a meaning. So what we were able to prove is that considering that we have, and we distinguish two cases, the degenerate case, meaning that the exponent is positive, bounded and positive, so the A2, and the second one, considering negative exponent, gamma, bounded negative, so it means that our equation is singular. And also we consider this regularity assumption on gamma. That was something new at this moment, because there's no extra imposition on gamma in order to prove existence and irregularity. And we were able to prove that under these assumptions, either for the degenerate case or to the singular case, the solution was Holder continuous if we started with a locally bounded solution, okay? But this A1 assumption, the assumption that gamma has to have this proper regularity, it seems too much. It was very demanding in the proof, so it was a technical assumption, and everyone, well, I don't know who everyone is, but several people that I was talking to said, okay, it is not a natural thing to ask for the solution. And some years ago, that thing was kept by the back of my mind. I was able to consider just the boundedness of gamma in the degenerate case and get the regularity assumption. So by assuming nothing about regularity on gamma, the proof of continuity was also available. The proof has to be a little bit different, but it was possible. But the same technique did not work for the singular case, so I could not avoid that in the singular setting. So a little bit further, I also work with the anisotropic porous medium. And in this case, I considered, so the exponents, mi's, I consider them to be positive and bounded. Okay, so this bar E stands for the maximum, and this bar here, under bar, stands for the minimum. And considering proper a notion for the weak solution, what I was able to prove is for the singular and the degenerate case you could have local boundedness, but I'm not allowing the mi's to have some mi's that brings the singularity and others that brings the degeneracy. So all of them should be greater than 1, and we are in this low diffusion range, or all of them should be less than 1, so the exponents would be negative when we are in the singular case or the fast diffusion. Okay. I don't know if you are quite familiar with the techniques related to this, but I'm just saying the topics that are major when proving the continuity, because this is the big issue and working on this. So what we want to do to prove continuity is to show that the oscillation goes to 0 as we are approaching the point. Okay? And by doing this, what we want to see is the following. Define a sequence of sets. Our sets will be cylinders because we have space and time. Okay? We are shrinking the cylinders to the point. As we are doing it, in each cylinder, we are considering an oscillation of the solution. So what we are saying is that as the cylinders are shrinking to the point, this oscillation is going to 0. And the way to do this is to, well, at least the way that I do it, is I go back to the technique presented by Di Giorgi in the 50s for elliptic case that was extended for the parabolic case in this case of nonlinear setting by Di Benedetto, and I tried to use this kind of technique to show that we can have this reduction of the oscillations choosing proper cylinders. These proper cylinders are what we call this intrinsic scaling. So choose cylinders, so choose a dimension in space, choose a dimension in time, in order that your equation behaves well, and you can then do the procedure that is related to this reduction of the oscillation. And there are two major, at least at this point it was the case, two major important estimates. Energy estimates like Cacciopoli estimates and logarithmic estimates that are very technical. And once we get these bigger estimates, more or less everything goes well. I say more or less because there are, of course, things that we cannot avoid. Well, the thing that I did here, I did separately for the singular and the degenerate case. But along the proof, the constant will depend on this oscillation. So it will depend on the solution. So I could not present a modulus of continuity. I could say that it is Holder continuous, but I could not say how this Holder continuity goes. Recently, I went back to these anisotropic PDEs, and I started to work with Simone Ciani, that is currently at the University of Bologna, and with Igor Shripnik, that is from the Academy of Science of Ukraine. And we started to work with anisotropic P Laplacian. And the anisotropic P Laplacian asked us to work with different PIs. So we needed a different Sobolev spaces. This is not new now, okay? This is quite known at this moment. So we have this bold P that stands for the vector of all PIs. So when we ask for a function to be here, what we are saying is that it has to be integrable, and its gradient also has to be integrable. So the gradient meaning only the space derivatives, the vector of space derivatives, and each partial derivative has to be in the corresponding LPI. Okay, and it's something that we always have to have, is this kind of Sobolev embedding. And in this setting of anisotropic spaces, what is known, and it is available, is this estimates that says if you can relate this exponent q, as it is written here, where this p star represents the Sobolev exponent when considering p, being p the harmonic average given here, what we can have is a relation between this LQ norm of V and this L infinity LS and this LPI, but now not for the V, but for the V at the exponent alpha I, when we are asking these alpha I's to be non-negative numbers. Okay. So once again, what do you mean by weak solution? Okay, set that kind of initial start point. What we could prove was that with this notion of local weak solution, we were able to prove Harnack type inequalities. And from that Harnack type inequalities, we could present how the solution decays. Well, how do I say that the solution decays? We are just working in the singular case, so all PIs are less than 2, between 1 and 2. And in those range, what was already known was that there was a time after which the solution is 0. So how is she getting down to 0? That is the estimate of the decay rate. That's one of the things. And we also got it for the anisotropic for the anisotropic porous medium equation. The same kind of results, more or less the same kind of techniques. To be real, or to be accurate, it was not for the prototype equations, but for a wider class of equations that is given here by this identity 1, where we are asking for these two operators, capital A and B, to satisfy proper structure conditions. So if this C here is 0, what we have is the prototype, more or less, because we can have something that is related with the prototype given by these two, let's say, elliptic condition and growth condition for the operator A. So what we got was these Harnack type estimates. Just in a few words, Harnack says that you can control the sup of a solution by its inf. Okay? These L1 estimates, that is called the integral form of Harnack estimates, that says that we are not saying that the inf of U is controlled, the sup is controlled by the inf of U, but the sup of the L1 norm of U in space is controlled by the inf in time of the L1 norm. That is why it is called a version of the Harnack, okay? And then another one that is quite common in the literature is to say that you can control the sup by the L1 norm of the solution. Having these two possibilities, we can then get the decay rate. Once you know that there's a time after which the solution goes to 0. That was known for the anisotropic P Laplacian, but it was not known for the anisotropic porous medium, and we proved that T star exists. So that was the time after which the solution is 0. And we did it in 2 different geometries. Let's say the standard geometry, that you use the usual cube. So what we are saying is that in space what we have is a cube of radius, in this case rho, and this new intrinsic geometry that says that you are not working with such kind of cube, you have to do something in space that is related to anisotropy presented by the equation. Okay, so why to choose this kind of intrinsic? Are we getting something that is nastier just to show off, something like that? And it is, well, it could be. It was something that is always available for everyone, but it has a double meaning. Just to have homogeneous estimates is quite good. Homogeneous estimates meaning that the MIs or the PIs no longer appear. Somehow we can take them back to the geometry and they more or less disappear by the end of the estimate. Or we can have a bigger or wider setting where we go back to something that Barenblatt did so many years ago, and we look for this context of self-similar solutions. What does that mean? Consider three, well, not three, n plus 2 constants, positive constants, these m, li's, and t, and consider a function that depends on the other by the relation that is given here. Okay, so you put u over m, and then instead of having x, 1, x2, whatever, you are putting something, this L1, x1, okay? And then instead of having just the time t, put a capital T and see what happens. If you ask the two functions to be solutions, let's say to the prototype of the anisotropic porous medium equation, what we are saying is that we have the time derivative for u somehow related to the time derivative different times, right? For V, and since V satisfies the anisotropic porous medium, we have this, and then if we compute these derivatives regarding the y's, what we have is something like this. So we get this extra. But we want U to satisfy the same equation. So this red expression here has to be 1. And then we get a relation between these constants that we introduced. And by saying this, if we are asking, let's say, to have the conservation of the mass, what we are saying is that this very simple cylinder, this Q1 here, so we have at the basis, we have the cube, and then we have the time interval 0, 1 for time. What we have is that we are transforming this Q1, if you are just taking what is given there, by this new one. So what we are saying is that in each I direction, we are considering different intervals. Okay? If we are considering a different Li that comes from here just for a proper choice of this capital T, what we have is different things, but now we are having something different in space and something different in time. So these two geometries are possible, available, and there are several other more. And what we can say is that these kind of new geometries, they leave the energy estimates invariant. That is quite good. So both of them work. The first one says that if we consider small m's, then what we have is that all the space intervals are stretched. Okay, but they do not preserve the volume of our cylinder. For the second one, we cannot say that all sub-intervals are stretched, because some of them are shrinking, some of them are getting bigger, but the volume is preserved, and that is something that we would like to have. So we choose the second geometry, and then for a particular choice of the A and the M appearing them, we worked with this kind of, let's say, calligraphic K of rho, saying that it depends on what happens in time. So this T here is fixed, okay, divided by this rho square. It is something that we would more or less expect it to have, because we are having these two derivatives in space for one derivative in time. And then this M appearing here is just the average. So some of the MIs are above, some of them are below the average. So this could be positive or negative, it depends. Okay, so what happens, and I'm more or less going to my point, is that if we are considering the intrinsic geometry, what is the price to be paid? Well, we have the possibility to say that we can have this L1 Harnack, so the soup is controlled by the inf of the L1 norm, okay? When having just rho, we are comparing to the 2 rho, and we are getting this extra term here. This is related to the fact that we are not working with homogeneous equation. So we have that capital B appearing, okay? And this is something that we have in the isotropic case, so it's quite good. So the geometry brings us to something that is not depending on the MIs. Everything here, so this lambda do not depend on the MIs, and this M, so it's the average, so it's a constant, right? It is not something that is changing in each direction. I have to say that if we are considering all MIs to be the same, we are getting what is known for the porous medium equation. So in this case, it is a good result. We are going back to something that is already known. If we are considering the standard geometry, what we have, so sorry for the green, at my computer it worked just fine. We have something that is simpler, as to say something about the kind of radius that we have to choose, but the price to be paid, okay, we have the soup of the L1 norm controlled by the infant of the L1 norm, but then we don't have something that is, let's say, I independent. We have to sum all of these. And what happens is, having something like this, there's a price to be paid when we are going to get the decay rate. So there's an extra effort when considering simpler geometry. So there's this payback. Choose something simpler, but then there's a price to be paid. If you choose something more, I would not say advanced, but more related to the problem, then it will be simpler. But, okay, it's not everything are good news. With this anisotropic geometry, what happens is that when we are getting this decay rate, when we are approaching the time for which the solution goes to zero, some of the sub-intervals, some of them are becoming quite big. So we are getting out of the cylinder. So at a certain moment, what we are saying is that near this extinction time, it's not that good, let's say. Okay, so just to finish my presentation, I'm just talking a little bit about what we are trying to do now. So what we are doing now is mix all of the two anisotropic equations. So this is a blend between the porous medium and the P-Laplacian in the anisotropic setting. What we are trying to do is to prove several results, several regularity results. So I would say that this part is the several open problems, and there are so many other open that we are not addressing. So what we want to do is to do this expansion of positivity, meaning what? Expansion of positivity says this following. We are working on cylinders, right? So fix a time level, and consider the cube that is located at time level. If you know that the solution satisfies something on that cube, can you say that it satisfies something alike in a cylinder that is centered on the top of our cylinder? So you can use it in order to prove regularity. That's more or less the thing about expansion of positivity, what it means. So that is one of the things that we are working on. So I would say that this part is already done. Having this at hand, we can prove Hölder continuity. We just have to see how, because this is the major tool in order to get Hölder continuity. Our approach of getting this reduction of the oscillation in smaller and nested subcylinders. Another important thing is to have Harnack. And once you have Harnack, you can use it also to prove regularity results. Harnack type estimates are easier to obtain at Harnack, but we are trying to do this. We are almost done for a part of it. And then prove boundedness once again, and then get some expression for the subpotential lower bound of our solution. So this, I would say, this is a major project that has several things, but once we can have all of these, more or less we are saying the old story about regularity results related to these doubly nonlinear anisotropic equations. So thank you so much for your attention.
Thank you very much for your really clear talk. And do you have any questions, remarks, comments? So, okay.
So thank you, Ulrika, for your presentation. In this list of ongoing projects, do you think it would be possible to consider a function in front of the...
On the right-hand side?
No, on the left-hand side, on the spatial derivatives? On
partial
the
derivative?
divergent, can we have a function dependent on x with some properties accounting for different spatial scaling in the problem of porous media?
Yeah. I would say that once we have something, I'm going back, sorry. We can have something more general like this, but then we have to ask for the operators. So instead of considering this A to be that kind of prototype that I'm presenting there, we can ask for something, but then it has to satisfy proper structure assumptions in order to get the estimates that we need, because we will try to need to control what happens in space, and in order to have that, we need this kind of elasticity condition and growth condition. So we can ask for to have something more, but it cannot be anything. Okay.
So, okay, then we can talk perhaps because I would be interested in some kind of description in which we have very different spatial scales in this porous media problem.
Okay. So this anitropic setting, precisely.
Perhaps.
Perhaps. Okay.
Thank you.
Any other questions?
Naive question, and if the situation goes wrong, does the solution explode? What happens?
Well, that is precisely what we mean by singular. We are allowing the solution the solution to explode. Oh, well, no. No. We are allowing the diffusion to explode, because here the diffusion is given by this. So when we are in the singular setting, meaning that all mi's are less than 1, this exponent is negative. So at the points where u is 0, that we are allowing it to be 0, this goes, right? It explodes. But the solution, no, because our starting point is that the solution is locally bounded. Okay, we need that in order to control the oscillation.
Other questions or remarks? Okay, if not, let's thanks Eureka again.
Thank you.
Next speaker of this morning section is Eduard Ortega from Norway, NTNU University, Trondheim, I don't know the pronunciations, correct? He's going to talk about rigidity of LP operator algebras. Thank you.
Thank you so much. First, thank you to the organizers for allowing me to come here and talk. And actually, it's a fantastic place here. It's one of the nicest auditoriums I ever taught in, so it's really a privilege. Okay, so I'm going to talk about, well, some of my research topics that I thought it would fit better in this conference, that is LP operator algebras, and some results on rigidity. So, well, I'm just going to bit overline of of my talk. First, I'm going to talk about a little short introduction what is an LP operator algebras. Actually, the examples that probably are more interesting and have further applications are the ones associated to groups. And then I'm going to give like the main technical tool here, that is why in the LP operator algebras, in particular in the case where P is not equal to, they have these nice rigidity properties. That is due to this a theorem from Lampertis that established like the structure of invertible isometries in LP spaces. And at the end, I'm going to give actually the result about rigidity, and I will try to explain what I mean by rigidity of group algebras. Okay, so let's start. So, what is an LP operator algebra? An LP operator algebra, man can think as a Banach algebra that admits an isometric representation in some bounded operators on an LP space, where P is from 1 to infinity. So one of the most famous results in operator algebras is the one due to Gelfand, Neymark, and Siegel that somehow internally characterize this L2 operator algebras, saying that whenever we have a Banach star algebra that has this condition on the norm, that's called that when you take any element, you multiply by its involution, and you make the norm must be equal to the norm square of the element. So this equation that looks like very innocent is telling you that this algebra is automatically some bounded operators on some L2 space, so Hilbert space. Okay, so this gives you a nice internal characterization of the L2 operator algebras, but unfortunately this characterization is not valid anymore, or we don't able to find any characterization of LP algebras where P is different than 2. So we don't have any kind of internal characterization. So we have to, it's more a constructive way. So we detect when an LP algebra is such when we actually can write down this isometric embedding into bounded operators in LP space. So when P is not equal to, the operator algebras lack of the nice properties of the C-star algebras, the L2 algebras. One of the most important things are that they don't have the norms usually are not unique, and the image between algebras, continuous image, the image of continuous morphisms are not contractive, something that is automatically in the case of P equal to. Okay, so the case when P is different than 2 is the one that we actually going to focus, because it lacks a little more theory, and the theory is not like as nice, as rich as the P equal to. No. So, okay, group algebras. So what we're gonna make is a construct LP algebras, operator algebras, and the most standard way to do it is giving an object and having a representation on an LP space, and from there construct the algebra. So in our situation, we're gonna take our favorite locally compact group, and actually we're gonna have as well a continuous cocycle satisfying the cocycle conditions, and then we're gonna construct a representation of this group together with the cocycle as a map from the group into the isometries on a certain LP space, satisfying these properties. Observe that the pi is almost a group homomorphism, but the problem is that is this factor here that avoids this to be a group homomorphism. Okay, so yeah, and this thing as the isometries of an LP space that we can define them as the elements such that they are invertible, and both the element and its inverse has norm 1. Okay, so I want to give a motivation of well, where these projective representations shows up, and probably, well, this is the example, and probably they come from, a typical example comes from this, from the well representation, and actually this comes from probably the most famous equation in mathematics, that is the Heisenberg commutation relations. Okay, given two self-adjoint operators in L2, they have to be unbounded, satisfying this commutative relation. Okay, so example of this of operator satisfying this property could be like this this Schrodinger representation of these operators that gives like an operator here. You just make the multiplying by the variable, and the other operator is the derivative operator. Okay, these are not bounded operators, but what we can do is exponentiate these operators, and we get like bounded operators. Okay, so we exponentiate these operators P and Q, and what we get here are unitaries. Okay, that depends on a parameter X and Y. So now these are unitaries, so invertible isometries, you want to think, that satisfies this commutative relation. Okay, this is called the wild commutative relation. So once we have that, what we can do is construct a projective representation of the group R2 in this following way. And actually we see that it's projective because the cocycle that appears before can be described in this way. Okay, so the projective representation somehow appears naturally in mathematics. So what we're going to do, but we're going to, given a group, we would like to construct a canonical representation of the group. Okay, and the way we do it is so defining this what is called the left regular representation. So it's a map from G to isometries into LP space of the group G. So the SP integrable functions in G. So what we're doing is essentially what this represented does is when you have an element from the group X. So this defines the isometries that mainly what it's doing is the translation of the function by multiplication of the group on the left side. So what it gives you, this representation integrates to a contractive star algebra representation of the L1 as bounded operators on LP space. And actually what we're doing, well, this is an algebra, the L1 G is an algebra with this somehow twisted convolution product. Okay, so we have this L1 is a structure of Banach algebra. And then what we're going to do is define our algebras that we are interested in. And those are like first the pseudo functions. The pseudo functions are just the completion with respect to the operator norm of the image of this L1 algebra by the regular representation. So this algebra has nice features. One of these is that we say that this algebra is always unital if and only if the group is discrete. Otherwise, this algebra is not going to be unital. We will see that it gets some trouble in our way. So to avoid the lack of unitality, we're going to define what is another interesting algebra. That is the algebra of convolvers. In order to do that, we're going to define we take the image of this L1 algebra we have defined before, and we do the double commutant. Okay, this double commutant is closed in the norm topology. This is a closed Banach algebra, but the nice thing here is that it's always going to be unital, because the identity operator is always going to be in this algebra. Okay, perfect. So now the question is how much of the group this algebra remembers. So you have this combinatorial object, if you want to think, and you create an algebra. So it may happen that the algebra forgets completely the group. Okay. So this happens sometimes, but not always. So for example, you have two locally compact groups, and we just say, like in the case that twist is trivial, so we just, for the easiest example, we know that the L1 algebras are isomorphic if and only if the groups are isomorphic. So in essential, this L1 algebras remembers the group. But and this is somehow with the exponent being equal to 1. But what happens when the exponent is equal to 2? This is what is called a sister algebra, the group sister algebras, reduced group sister algebras. And in general, the group sister algebras forget the group, in a sense that two different groups can give you isomorphic sister algebras. So example, this kindergarten example is the cyclic group with 4 elements and the group with 4 elements and 2 torsion. So, but there's some example, some class of groups where the sister algebra remembers the structure, the groups that are torsion-free and abelian. Then the algebra remembers the group, but in general it's not true. Also, there are some nice examples where we have the free group, where the group sister algebra is the free group, actually separates the free groups. And this is to use some other techniques due to like K-theory. So actually what you can compute is the K-theory of these two algebras, and you say they are different, depends on the M and N. So somehow they distinguish the groups. Other examples come from more von Neumann algebras, but I'm not going to go there, where actually this rigidity is, so this is what we call rigidity, okay, that it's actually very rare. Okay, so how we deal the problem in the case. So actually the idea is we want to give like our algebra some invariant that somehow is going to recall the group, that carries with it the group. And these are going to be the group of invertible isometries, or the unitary group of a Banach algebra. When you have a Banach algebra, you define the groups of the unitary group as the elements that are invertible and the norms of the element and the inverse are 1. Of course, important thing here, we need unital, because otherwise invertibility does not have sense. So, so that's why we need to work with this the algebra of convolvers, because it's always unital. We're going to deal the general case of locally compact groups, because if we could just do the same here with the algebra of pseudo functions, but we have then to restrict to the case of the group being discrete. But we don't want that. So actually what we're going to do is the unitary group of the algebra convolvers is remember that this can be represented as a bounded operators in an LP space. So this is just precisely the intersection between the convolver area, the convolvers and the isometries of LP spaces, invertible isometries. And here is where it comes in play this nice theorem due to Lampertis in the mid-50s that characterize invertible isometries in LP spaces where P is different. And well, I just denote essentially. I'm gonna say what the heart of the theorem says that okay, when P is equal to 2, there are a lot of isometries, and essentially because you can rotate elements of the basis. Okay, and this is due to the geometry of the unit ball. In P equal to 2, the ball of so this is the element with norm is more than 1, has a nice geometrical shape that is like a circle, but for example, with P equal to 1, the elements, the unit ball has this geometrical figure. This means that, observe that you can translate, you can rotate elements here that they will keep preserving the norm. But here, you cannot rotate. Because if you rotate elements, the norm is not norm preserving, so it's not an isometry. So essentially, Lamperti's theorem is that isometries in LP space with P different than 2, what is 2 essentially is a permutation of the elements of the basis. Okay, and scalar multiplication. You cannot rotate elements. And and not only this, what it's telling you is that, okay, when you have two invertible isometries, the distance between the two isometries is gonna be big unless you don't have the same rotation or the scalars you're doing are very close. So this will avoid a lot of homotopic equivalence between isometries. So this is what exactly gives you the rigidity that we want. So then we have our result. The result says that when you have a locally compact group G, you can compute the unitary group of the algebra of convolvers. And this is just what is called the Mackey group. I'm not gonna just comment the definition, but essentially as a set, you can think is a product of the group G and the unit and the elements or complex numbers of norm 1. So what do you think? If you think the representation, what is this? These are gonna be are gonna represent the isometries that moves. So you make a permutation between the elements of the basis. And this element here, the scalar is gonna be like the scalar multiplication. So you just multiply by an element of norm 1, so it's not changing. So this unitary group actually recovers very nicely the group structure. And of course, then you make like the homotopy between all these elements, This result is telling you that the homotopy is going to be only homotopy elements when the scalars are very close. So in a sense, what you make homotopy equivalence between the unitary group, the only thing is that you're doing it, but the groups are going to stay there. So what this is giving you, is the following. Once you are able to determine the unitary groups, that essentially keeps with them the structure of the group. Well, this isomorphism is not only an algebraic isomorphism, it's also topological. Okay, so you have R isomorphic as a topological group, and you're using here the norm, the topology given by the weak star norm. So what you have here is that the result is that whenever you have an isomorphism with the groups, and actually this cocycle are equivalent in the two cohomology group, then what you have is that the algebras are isomorphic. So this direction is clear, and the other direction is the nice result is that because isometric isomorphism between these two algebras gives isometric isomorphism between the unitary groups. So then you can recover the structure of the group in this way. And this is no problem because this algebra is always unital. In the case of this, remember that these algebras are not generally unital unless the group is discrete, so we don't have this characterization. But we do actually some trick here with the algebra of multipliers, so we can actually extend these results anyway. Okay, but so essentially the rigidity result is telling you that the algebra of convolvers, when P is different, this is important, P must be different than 2, because otherwise we don't have Lamperti's theorem. So we have somehow this kind of nice rigidity. And examples as well related with the initial example that is I just put is this wild commutational relations. When you can have a representation of the Z2, and you can just giving like a number, you can define this cocycle, and then define this algebra. Okay, the twisted algebra Z2. This is a very known object called the non-commutative tori. Okay, the tori is extensively used in non-commutative differential geometry, but also in, for example, time frequency analysis and so on. And this gives like this result is telling you that this isomorphism, these two non-commuted vectors are going to be isometric if and only if the cocycles are cohomologous, but this is equivalent to saying that the difference between this scalar here we define must be an integer. This is contrasts very much with the case where the C-star situation with p equal to 2, where you can find isomorphic algebras that the parameters are not cohomologous, and definitely contrast with the case with the convolvers algebra, the von Neumann algebra case in a sense, where all these algebras are always isomorphic to the hyperfinite factor, to one factor. Okay, so yeah, so I think that's all what I wanted to say. Thank you so much.
Okay, thank you very much for your talk. And do you have any questions, remarks, comments, solutions? Okay, if not, I have just a small question because, okay, you talked at the beginning about the Gelfand-Neymark theorem. Any subalgebra, C-star algebra can be seen as a subalgebra of the boundary linear operator on the Hilbert, no? That means the representation you said before, no?
Yeah.
Yeah, but okay, yeah, it's a new problem about instead to consider just subalgebra, there is an open question about if you can see any Banach algebra as the Calkin algebra of a Banach space, not Hilbert.
Yeah.
You know, this kind of, like, okay, Motakis proved that any abelian C-star algebra is star isomorphic to the Calkin algebra of a Banach space. But do you know any other C-star algebra so that you have a representation as the Calkin algebra?
Yeah. No, I would say some results, but it's on commutative.
Okay, but commutative is already solved. Okay.
Yeah, you can use this kind of Gelfand theorem to have like a subalgebras of some on some continuous functions on a topological space.
Yeah, okay.
But
commutative is already solved, but yeah. No commutative. The problem is in non-commutative.
No, non-commutative. I'm not aware, and I don't think there is any nice representation of these algebras.
Okay, thank you. Any other questions? If not, let's thank the speaker again. for the next speaker is José Luis Cardoso from UTID, and he's going to talk about from function spaces to Hermite Hadamard type inequalities associated with quantum operators. Thank you.
Okay, good morning. Let me put 20 minutes, not to override it too much. So I want to thank the organizers for the kind invitation to be here. For me, it's a special opportunity because I was a friend of José Carlos Petronillo, and in the beginning, especially in the beginning of my talk, I will explain the way I related with him, not the friend part, but scientifically, because I published with him only one paper in 2015. So I'm talking a little bit about that paper in the beginning. So during my PhD with Joaquim Bustos from the Arizona State University, a lot of years ago. I finished in 2000, and we developed some results involving basic Fourier expansions. It's Fourier expansions using solutions of difference equations related to the operators that you can see here. It's the classical, or some of the most known quantum operators. For instance, for instance, here you have the very known Q derivative, or the Jackson derivative. Here it's the Hahn quantum operator. The previous one, it's a particular case of this one when this parameter omega is 0. And in my PhD, I dealt with this operator, which is, it's more symmetric in a certain point of view, but it's more or less the same. It's equivalent to with this one, with the Jackson operator. We have then the inverses, of the corresponding inverses operators. For instance, here you have the Jackson Q integral. Here it's the inverse of the Hahn operator, Jackson Thome or Thome Norland, something like that, usually known. Notice that, for instance, in the Jackson operator, that the points that in an integral between A and B, the points, the discrete set of points that are used are the points of this form, B times Q to the power of K. Q is a fixed parameter between 0 and 1. We fix that because we want to deal with the convergence results. And so these Q integrals use a discrete set of points, and they are related with, in the case of the Jackson operator, they are intrinsically related with a very important point, which is the 0. It's an accumulation points for the discrete set of points that are used in the definition of these Q integrals. In the case of, for instance, of this more general integral, the point is this one that you have here, which is the omega divided by 1 minus Q, and Q is between 0, a real parameter between 0 and 1. The previous trivially, you can see that these operators, when Q goes to 1, in the Jackson case, you obtain the classical derivative at point x, of course, when it exists. So what we deal, as I told in my PhD in the years that follow, we study properties that are needed. For instance, the functions, the Q exponential and the Q sinus and Q cosinus. They are solutions of Q analogs of the classical initial value problems using the previous operators, the Jackson derivative or the Hahn derivative. So it's quite similar. The results need other techniques different from the classic ones, because the Q sinus and the Q cosinus, for instance, they are not periodic, they are not bounded. So the way to deal with it is different. They are similar, but the techniques are different from the classical case. So we, and later after my supervisor, Joaquim Bastos, he died in a car accident. And so lately, after this, I worked alone for some time, and I published a paper in 2011 in Journal of Fourier Analysis and Application with a result that some other results, of course, that are needed, but this is the most important one in that publication, that it's a much simpler way to give a sufficient condition to obtain uniform convergence of the basic Fourier expansion using the Q sinus and Q cosinus functions. So with this definition, that it's I introduce it with this way because it's very close to the classical Holder condition. Linear because it is related to a lattice that is Q linear, and the points that are the orthogonality relation that it's important to establish Fourier expansions. It's in the interval between -1 and 1, and it uses the discrete set of points of the form that is above, plus or minus because of 1 and -1, and q to the power of n minus 1 when n goes from 0 to 1. That it's just one point when n is 0 that you obtain a point that it's not included in the points that I told you, but it's just one point. It doesn't give any problem. So when I submitted this paper, the referee told me one problem that it was very good for me because I was not aware of that problem, that situation that was related to the monotonicity of the Q integral that I was using. Let's say it is very important to you when we deal with the integrals that when a function is less or equal than another one, the corresponding relation is maintained when you pass to the integrals. It's a monotonicity property. So he told me that I couldn't use the Holder inequality in the paper, and he sent me an example where he showed me that we have a function that is less or equal than the other, and if you compute the Q integrals of these functions, the relation inverted. So that was a problem, but I told you, well, I don't use in the paper the Holder inequality in its general form, what I used, it was the Cauchy-Schwarz inequality, and that one is valid because I started with an inner product defined by the Q integral. So I took the norm defined by the inner product. So I can always use the Cauchy-Schwarz inequality. So the referee stand a little bit, well, that is, maybe this is true in this case, in this particular case, because you are computing the Q integral between -1 and 1. But he agreed with me that what I used, it was correct. So the paper was published in 2011, but that question, some time later I thought about that question and tried to obtain some results, or to know, for me to at least to know much more about that. So I studied that problem, and it is what the results that in the beginning I obtained, but then I contacted José Carlos Petronilho from Coimbra, because at that time it's a small university in the north of Portugal, we didn't have access to the basis of the publication, so I developed some results, sufficient condition to obtain the monotonicity property, but I didn't know if that was already published. The referee in a certain way told me not, but some years, 2 or 3 years already passed. So I contacted José Carlos and told him I obtained these results. I sent him by mail, can you help me looking for if someone already studied this problem. So we involved in this problem, and we studied that problem, and we published the paper in 2015. It was not easy to publish the paper because the monotonicity property holds when you compute Q integrals between 0 and 1 in the normalized case, or between 0 and any positive number. Or also in the other side, from a negative number to 0. 0, it's the important point. It's the accumulation point of the discrete set of points used in the definition of the Q integral. So the results that we obtained, a sufficient condition, it was the monotonicity property holds when the A and B, the points of the integration between A and B, the A and B stands each one for the other side of the 0. I mean, A less or equal than 0, less or equal than B. A can be 0 or B can be 0, but this is the right condition to. So, and that was that paper that related me with José Carlos, and later I developed other results. José Carlos was still alive, but he had another idea to study that problem using general measure theory. I told him, but that way you are going to lose some restrictions and some interesting, looking at that broad looking, you will lose some important. and he said, okay, so then publish you. And so in 2019, I published alone a paper in the continuation of the previous one with José Carlos Petronilho. So the condition, it's as I told them, the monotonicity problem property of the Q integral. It's this one, as I told you, when the A and B satisfies this condition, then if F is less or equal than G, that we have this problem. So that property. So with this property, then to prove the general Q holder inequality and then the Q-Minkowski inequality, the proof can be done just like in the classical case with the above property. So this was the result, the main result, or the starting result that we proved, and then we established a link between the Jackson integral and the Q omega, or the inverse operator of the Hahn derivative. A link, at that time we thought that the link was new, but then one of the referees told us that someone already published the link between the two integrals. But anyway, our link in the paper with José Carlos, it was a much simpler one, very friendly. The other one, it was not very friendly. So with this stuff, we were able to generalize some results to the results. These results were already known if you use integrals between 0 and 1, or 0 and a positive number. So with this condition, we could generalize these results. And this part is new, the reflexive property. The rest is similar to what was already known, but with the extension not necessarily working between 0 and a positive number. So you can use any A and B. You have only to satisfy the accumulation point must be between the limits of the integration. So with this, then we were able to extend with the link between the two integrals. We were able to establish a similar result for the case of the let's call it the Hahn integral. It's the inverse operator of the Hahn derivative. So we were able to prove the monotonicity property, then the Q omega holder and Q omega Minkowski, and then just the similar result, but in this case for the Q omega integral. See? Just in the same way. So then in 2015, that is the part that I've been working in the last years, a group just introduced, it was for the PhD of Anna Shihata in the north of Africa, and they introduced this general quantum difference operator related to this function beta the t. The function beta must satisfy this property, being continuous and strictly increasing. And this is a nice way to look at all the previous operators, because if you take this beta function equals to q times t, q fixed between 0 and 1, you obtain then the q derivative, the Jackson derivative. If you take this beta function to be q times t plus omega, then you obtain the Hahn derivative. And so you can, this is just a way of looking that generalizes and puts all together all the previous operators. So is the remark just below. It is clear that the Hahn operator corresponds to the choice that I told you, q times t plus omega. And this is an important point. This is the fixed point of this, in this case, of the Hahn operator. In the case of the q derivative, it's 0. Here it's this one. When omega it's 0, you obtain the Q operator or Q derivative. And all the things that I told you related to 0, now it must be given in terms of this fixed point of the above function. Then this is just the definition here of the inverse operator, the beta integral. So just it passed 20 minutes, so I just at this moment I try to in 5 minutes to just give you just a general view. So I will pass faster. For me, it was much more important to speak, as you noticed, a little bit about José Carlos because, what we were able at that time, I published this alone. I tried to convince José Carlos, but he said, no, do it yourself, and he didn't want to enter. I proved that similar when the fixed point of that general quantum operator, that is this one, is between 0 and b, then you have the monotonicity property. So you can then, as a consequence, prove the beta Holder inequality and beta Minkowski inequality, that it's important. This is important results for us to have linear spaces and to study properties. So these are the fundamentals, the basic fundamentals. Then I proved that a similar result for this general quantum operator. It's very similar to the previous one. The techniques, just the part of being reflexive, it was a little bit more hard, but it's in a certain way it was similar to the previous one, the way to prove this. So we have also the classical results, or the Q analogs of the classical results, the beta analog of the fundamental theorem of calculus. Here it's when the function f is continuous, it's just, you can see that it's very similar. So here it's the beta analog of integration by parts formula. Then later in 2021, I introduced this an analog, a beta analog of the classical Sturm-Liouville problem with separate time conditions for the previous operator. And these are some results that I needed to establish the properties, to define. Then later in a paper with Shihata, we introduced the beta directional derivative and a result related with that, the beta gradient vector. This is very similar notion, so I will. And then more recently, I published a paper with Shihata, where for this, the beta integral, we prove analogues of the classical Hermite-Hadamard inequalities. So this is some results related to that. And then we applied it to all the operators that I told you, the Jackson Q integral, the Jackson Q omega integral, and the Norland integral. So I will finish my talk right now, and I'm sorry for the time.
Thank you very much for your talk. And do you have any question or remarks or comments? Okay, if not, let's thanks once again the speaker. And now we have coffee break. We will see here in 30 minutes, okay? Enjoy your coffee break.
Audio Jungle. Audio Jungle. Audio Jungle. Audio Jungle.
Sciences, whose managing editor is Professor Alexei Karapentias. We plan to publish at least 2 volumes, 2 special issues of this conference in this journal. We are expecting to have around 20 publications between the 2 special issues. The topics will be the topics of the conference, like ranging from classical analysis to modern analysis. And the type of publications that we expect is both research articles and also surveys and reviews. Yeah.
Okay, I will say some words. Some years ago, we